In most high school math classes nowadays, quadratic equations are introduced along with this formula, the quadratic formula, the scary formula. Why does it look scary? I mean, for anyone who's used it many times, it's just become familiar. But when we get introduced to it, it is quite scary. I mean, come on, you've got two solutions, you get a square root in there, it's all in a fraction. I mean, you've got to consider context. Before that, most of the time, the hardest piece of math students have ever done is Pythagoras or linear equations. And I mean, the quadratic equation is completely different. I mean, you can try to solve it with linear methods. You could first try to isolate ax squared. So you bring bx and c to the other side. Then you want x squared on its own, so you divide by a. Okay, it's starting to look a little more complicated, but it's still manageable. And then get rid of that squared term. Well, we can take a square root and add a little plus minus in the front to get our two solutions. But now, we've got a really big problem. I mean, we're doing all this to solve for x, but we've got x in terms of itself. So that's not going to help us to get anything definitive. We're going to want to visualize. So, first, remember that to plot an equation, we use this xy coordinate plane, and we consider a relationship between points, right? Every point in here is defined by an x-coordinate and a y-coordinate. So if I, for example, want to plot y equals 5, I get all the coordinates with the y-coordinate being 5, all those points. So see, the y-coordinate doesn't change. And I can do the same, I can say x equals 5, and I get another line, but vertical. And here we've got the point 5, 5, where both x and both y are equal to 5. That's the basics of plotting. So we can get something a little more interesting by looking at a linear graph, of course. And this should all be familiar to you, hopefully. And if I play around with these coefficients here, I can play around with a, and that changes the growth rate or the slope. See that when a is equal to 0, it doesn't change at all. When it's negative, it's decreasing, and when it's positive, it's increasing. And when b changes the so-called y-intercept, and it's easy to see that when x is equal to 0, this term goes away, and we're only left with b. So here at x equals 0, we're always going to have y equals to b. That's not too hard to see. Now, this is easy, but quadratic equations tell a completely different story. In fact, as we go up in degrees of polynomials, things get always increasingly more complicated because we get more coefficients to deal with. More coefficients mean more freedom, which often means more complexity. So let's set this to 0, let's set this to 1, let's set this to 0. Alright, so let's see how the terms are going to affect our parabola. So first of all, you have to consider that this x squared here, as x grows, is going to grow a lot faster than x, or just nothing. So you can already predict that this a term is going to predict how fast our parabola grows, because it's the x squared term that really defines the growth of our parabola. And in fact, when you play with a, you see that this is true. And again, if a equals to 0, we've got nothing, and of course this isn't going to be true if I increase b. This is where I'm going to get a linear equation. But when we talk about a quadratic equation, we always assume that a is not equal to 0. Otherwise, it's pretty useless. So yeah, I can play with that, and I can get a growth rate. And see that when it's negative, it opens downwards. When it's positive, it opens upwards. So that can be kind of interesting. Now, then I can switch to b here and play with it. Now, it's a little less obvious what's happening here. And the main thing you have to try and see is that it doesn't actually change the shape of a parabola, but it just translates it around. I mean, you could be proving this by choosing arbitrary points on our quadratic and simply telling ourselves, okay, what's the x difference between them and what's the y difference between them? And then finding a unique pair of points in the new parabola as you change b to any other value that directly relates with the points you have before. And if you can define a unique relationship like that, then you can define a unique relationship of distance between your two parabolas, which show they have the same shape. And you wouldn't be able to do that when you're changing a. It's only when you're changing b. And then when I change c, you once again have a y-intercept because all the other terms go to 0 when x is equal to 0. So that goes away. So graphs are cool and all, but most of the time what you're actually going to see is equating this to some value, like this is equal to 1 or this is equal to 0. So looking back again at linear equations, we might consider ax plus b equals 0. And this line here is going to tell us the roots of this equation. Now I'm always going to be setting this to 0 because if this was some other constant value, I could just subtract it on the other side and change what this b value is. So this is for to stay general. So as I change a, this doesn't seem to change. As I change b, it's shifting around. I can change a again. It's still moving. I can do all kinds of crazy stuff. But we're always going to have a root, right? Well, except if I change a to 0. But once again, that's not a linear graph anymore. You just got a constant value. This is quite simple. You always get one root and it's okay. But quadratic formulas tell a very different story. Or actually, should I say, they actually tell the same story. If I plot this, and now I consider ax squared plus bx plus c equals 0. So first of all, two roots. Pass this for the x-axis twice, and you might have seen that before already, two roots. Now I can shift it around, but it's still two roots, still two roots, still two roots, and you may think, oh, okay, well, two roots is the norm, it's fine. Now I can shift this down, and bam, no more roots. Is there just no solution? Do I never have a point which satisfies that equation? Well, sure, you don't have a real point. And at this point, it's, with no pun intended, you might want to go into the complex plane in imaginary numbers to actually see that you still have two roots. That's not the purpose of this video. We want to consider the quadratic formula for real roots. And then there's the special case of, let's see if I set this to 0, this to 0, and this to 1. You get the special case where your curve is tangential to the x-axis. And so it appears like you only get one root. It turns out you get this root, but times 2 in some sense, and you get this root appearing twice in your equation. And so you've got a root with multiplicity 2, as they say. You actually have a more general version of this called the fundamental theorem of algebra, which is going to state that any polynomial, this is a polynomial here, of degree n, ours is of degree 2, the degree is just the highest power in our polynomial, is going to have n different roots. Here we see that you can have two real roots, two real roots. Looks like one real root, but it's actually times 2. And here we actually have two complex roots. It may seem like we're inventing things just to make our formulas work, but it really is useful. So how are we going to deal with that? How are we going to make one size-fits-all equation that's going to give us all our answers no matter what? If it's 2, if it's 1, if it's none for the real solutions, how are we going to get an equation that really fits that? So our main axis of focus today is going to be looking at the symmetry of its parabola, or its apparent symmetry. I haven't actually proven there's a symmetry anywhere. I've just established that there is a symmetry. And we're not actually going to prove that in this video. I'm going to assume there is a symmetry and find the coordinates of the point of symmetry. Now, from that, it's actually quite easy to prove that the graph is symmetrical. Once you know the coordinates of the axis of symmetry, you can just check that it's symmetrical around that point. And there you go, you've got a proof. But we're going to reverse engineer it, so just keep in mind that what we're doing with this video, it is not a proof, and if you want to prove things, you can do that on your own. Leave it as an exercise, it's always fun. So let's actually do that. Let's actually try to find what this axis of symmetry is, and then we're going to see why that's useful to us. So we can start by defining a function fx, which is going to be our quadratic, ax squared plus bx plus c. Now from that, we apply the definition of symmetry to that function. So we have some center point C, and so we want to check that if I move some distance x to the right of C, then I get the same value as if I move that same distance to the left, which is why I've got f of c plus x equals f of c minus x. Now I resubstitute the value of f back into that expression, and now I get a big long thing. Now I can subtract c from both sides, and I can also expand those b terms to get this. Then from here I can get rid of that bc and get to this. Now we may want to rearrange because we want to solve for c. So all those squared terms we're going to bring to one side to make things simple, and all the bx terms as well as the a we'll bring to the other side to get this. And note that we can do this, we can divide by a because a is not equal to 0 by the definition of quadratic equations. Then from here, we're going to expand those two squared terms to get this long expression. And now we get some things canceling out. The c squares are going to cancel out, and the x squares are going to cancel out, because remember, minus and plus makes minus. And we get to this. And from there, it's easy to solve for c. We simply divide by 4x. And we can do that because x is also non-zero. Because remember, x is the distance of symmetry that we're considering. And if x is just equal to 0, then we're only considering the point c itself. And of course, c is always going to be equal to c. And finally, we get a solution for c. C equals minus b over 2a. So at this point, we're going to want to gutch at our work. So I can set x equals minus b over 2a. And so this line here is really just plotting the x-coordinate of a point of symmetry. And as I move these values around, you can see that it follows a parabola. So our work seems to be valid. So now we can actually exploit this property of symmetry that our parabola has. And remember, in our video we didn't actually prove that it was symmetrical. You can do that on your own. So we're going to exploit that property because we know the roots are on the same, have the same y-coordinates. They're always equal to 0 on the y-axis. And that they're on two different sides of the axis of symmetry and that they lie on our parabola. That means that they have to be equidistant from the x-coordinate of our point of symmetry, right? So one root is going to be minus b over 2a plus some constant k, and the other root is going to be minus b over 2a minus some constant k. That's why we get the plus minus in the quadratic formula, right? Because we get two solutions. So we have to actually find that x distance. And the way we're going to do that is actually by first finding the y-coordinates of our point of symmetry. And we'll see why later. For now, let's just find the y-coordinate, and then we'll motivate why we did that. So solving for the y-coordinate, we've got a of minus b over 2a squared plus b times minus b over 2a plus c equals y. And you can already see that this is exactly plotting the point of symmetry, but we actually have to solve this to get a proper expression. So, well, simplify, not really solve, but anyways. So simplifying, we get a times b squared over 4a squared minus, well, plus, well, yeah, minus b squared over 2a plus c equals y. And so notice I really just expanded the, expanded the square here, and I brought the b inside. Now we can cancel these two a's here to get b squared over 4a minus b squared over 2a, not that, b squared over 2a, like this, plus c equals y. And we see we're still plotting the same line again, so we're still doing good. Now we can get a common denominator so that we can actually make one whole fraction out of it. So we get b squared over 4a minus 2b squared over 4a plus 4ac over 4a. So notice I just multiplied top and bottom by 4a. So these are still equivalent fractions. And plotting, we still got the right thing. Putting it all into one fraction, we get b squared minus 2b squared through b squared plus 4ac over 4a. And that's equal to y. Again, same line, so that's good. And we can actually take away these b squareds here because they cancel out. So we get minus b squared, like that. So that's going to be the y-coordinates for our point of symmetry. So now I can move these values around, and we've got the two plots following, just like we needed them to. So now, why is this important? Well, the roots, by definition, are always going to have y-coordinate of 0. That means that if I consider the difference in y-coordinates between the roots and the point of symmetry, it's going to be 0 minus b squared plus 4ac over 4a. And so the 0, I mean, we can kind of just get rid of because it doesn't really make any difference. We just get minus b squared plus 4ac over 4a, which is just going to be b squared minus 4ac over 4a, right? So that's the relative difference between the roots and the y-coordinates going up. Now we can exploit what we looked at earlier with our coefficients, where we realized that only a was impacting the shape of our quadratic, and that b and c were only impacting the position. But it was translating our quadratic, really. So we can argue generally by setting b and c to 0, just to make calculations easier, because since we're talking about relative differences between points, translating our graph around isn't going to make a difference at all. So we only need to look at differences in the shape of a parabola, which is when a varies. So we can consider that the axis of symmetry is then at the point 0, 0, or goes through the point 0, 0. And so at that point, the roots that we would have if we moved b and c, right, they would have coordinates of the y coordinates of the axis of symmetry plus b squared minus 4ac over 4a, which is what makes them be equal to 0. Now, if we keep that same relation, but set b and c to 0, we're not going to get roots anymore, of course. But now we're going to get points that have y coordinates of b squared minus 4ac over 4a. And so now if I solve for this new quadratic equaling this value, then I'm going to get an x value, which gives me the relative difference between the axis of symmetry, and the roots themselves. And then when I add those together, it gives me a general expression for the x-coordinates of our roots. So my new parabola here is just g of x equals ax squared. And it's doing the same thing, but if I move the other one, see, this one doesn't move. So that's going to be our new quadratic that we're looking at. And so I want to set g of x is equal to b squared minus 4ac over 4. Oh, let's be careful here. This, and divide by 4a. All right. So let's actually substitute in the expression for g of x. Let's keep this plotted actually. So that we get ax squared is equal to b squared minus 4ac over 4a. And that's an easy expression to solve actually. We can just divide by a at first to get x squared equals b squared minus 4ac over 4a squared, because we divide by a. And now to get rid of a square term, we do a square root. So we get x equals square root of b squared minus 4ac over 4a squared. And we need a plus minus here, right, to consider the negative and the positive values that would square to make that. And this is the same, actually, as considering square root of the numerator over square roots of the denominator. And the square root of the denominator is just 2a, right, because 2a squared is 4a squared. And at that point, that gives us the relative difference between our point of symmetry and our roots on the x-coordinates. And so now things should start to look familiar. We've got the x-coordinate of the axis of symmetry, which is minus b over 2a. And then to get one root, we can add this relative difference. And to get another root, we could subtract this relative difference. And if we want to write that in a more familiar form, see that they have common denominators, so I can just get rid of one of these. And at the top, just get minus b plus. And down here, minus b minus. And look at that. That's the quadratic formula. It really is. I mean, the quadratic formula is more concise. It's got plus minus, but it's exactly the same thing. And so we see that a formula which at first looks complicated can actually be fully derived by, well, by understanding what a parabola looks like, arguing by symmetry, and really just solving equations linearly. The only time where we didn't apply linearity was with this square root here. But that's an easy operation to take when we've only got one thing to square root. And so that's it. That's how you get the quadratic formula in a natural, visual way. At least to me, it feels a lot more natural than just it being fed to you in high school. And sometimes you'll see derivations where they complete the square, but I was trying to aim with this video to not complete the square because many students can find that daunting, even though in the long term it's really not that hard. It's just reverse foiling. But so hopefully this video was helpful in that respect in showing where the quadratic formula comes from.